Hello everyone, welcome to the third week of lectures in this course diffusion in solids. So, last week especially we looked at various diffusion equations on how to solve them using Laplace transform, separation of variables and so on. So, actually today's exercise is just to give you some idea of hands-on experience. The hands-on experience is not right now, but it is something that you can try on your own after you have done listening to this lecture, and you can generate the diffusion profiles by writing simple codes and see for yourself how the various parameters influences the diffusion profile. So, this is through a software called as Scilab. It is a open source software. So, today we will talk about introduction to Scilab, plotting of basic mathematical functions, carburization and homogenization concentration profiles. So, you might have heard of the MATLAB. So, this is comparable to MATLAB, but it is a free and open source software for numerical computation, and you can do matrix operations, data visualization, scientific computation and so on. You can generate various graphs of complex mathematical functions here, and it has a rich library of predefined function. It has a cross platform compatibility, and it is powerful for simulations and modeling. First thing, you just type scilab.org, so you will get an interface like this, and depending upon which system operating system you have, Windows, Linux, Mac, you can download and then follow the installation instructions. It is pretty straightforward. Then after you have opened the Scilab post installation, you will see certain windows in the Scilab, and let me just show you. So, here you will have a console where you basically you see this is like your command window, where you display messages, errors. You can type directly commands here as well. Then there is a variable browsers to in your code wherever you are using the variables. These variables are indicated here, and then you have a command history tab, which also allows you to see the history of the previous commands that you have used. Now, there is basically an editor which basically writes and saves scripts. So, you can type certain commands in console, but that cannot be saved. Whereas, if you use an editor, then editor allows you to save the files. So, you can save your codes for future reference, run them again and so on. So, this editor is the window which we will be using the most often. Then you have a graphic window, which is again where your plots are shown. So, whatever the plots you want to generate, the corresponding code you write in the editor, and when you execute, then you will be able to generate the graph. Now, let us go with a basic code. Please remember, the purpose of this lecture is actually not to give you a coding lecture, because coding lectures are separate. There are separate courses for that. Here the code I will just show you to just familiarize with to you how Scilab can be used, but the main purpose of this will be that once the code is written, how you can use it to basically understand the influence of certain parameters. So, anyways, I will come to that. So, let us see a very basic code in Scilab first. Let us say a very simple equation like y is equal to ax square. Now, so this is how your editor would look like, and you have this double slash to give comments, okay, so that you remember what is this function for. Now, let us say my function I want to is do a plot. It is a square function, so I put square of a. So, I define first the range for x. For example, I define here 10 to minus 10 to 10. So, I write x is equal to minus 10 colon 0.1 colon 10. That means this 0.1 is the steps. Okay, so minus 10, minus 9.9, minus 9.8, and so on. These are the values of x that it will take. Okay, so this is the how you define the range for x. What is the range of x that my variable can take? This is just a command to clear if there is any previous plot. As I said, you can you need not really memorize, but once you have gone through code, it is very simple to understand. You can write your own codes also. Then what we need to do is calculate the y value. So that for each of the x that we have entered, we calculate y is equal to a multiplied by, which is star, x dot. The x dot is used so that it multiplies with each of the x. Okay. So here not just one x, for each of the x you want that a is multiplied and then square is taken, or square is multiplied and then square is taken and then a is multiplied. Okay. So here a star x dot square. So this is the syntax. Now this is plotting the curve. So plotting the curve, you have simple function of plot x comma y. Now basically to give more features to your plot, we have label of x, which is very self-explanatory. You write it as x. Y label is y is equal to ax square. You will see the output, then you will realize what this means, and the title is curve for y is equal to ax square. So remember, this entire thing we have written as a function. So here it is the beginning of a function, here there is the end of the function, and the function name we have given is plot underscore square a. Now after the function is defined, what we write is that, remember, this a we have not given any value. Why we have not given any value? We want to ask the user to enter the value. So therefore we write a is equal to input, enter the value of constant a in the double quotes, and here the semicolon is to terminate the statement. And then finally plot underscore square a. So this is the function. When this function runs, it will run this here, and it will ask the value for value for a. So once you have written this code, what you need to basically do is use this button. So you can see here this button. This is called save and execute. So this saves the file with the .sce extension. Once you click this button, then it is saved, and when it executes, you will see that this function from here to here will be executed, and here when you come, a is equal to input, enter the value of constant a. So for the execution, it requires the value a. So for that, it will ask. So once you click save and execute, you will see something like this. You see, enter the value of constant a. This is a cursor. When you enter, let's say I enter the value a is equal to 1. Then what it gives me is the plot of y is equal to 1 into x square. Okay, so this is the remember, this is the label we have given for the title. This is the thing we had given for the y-axis. This is what we had given for the x-axis, and you can see the range minus 10 to 10. Now, what if I want to not enter only one value? I want to see how my graphs will change if I change this value of constant a, which is what actually is our intention for our diffusion profiles also. So let me show you another example, okay, which is y equal to a sin x. Okay, we are familiar with what is sin x. So here again, this is the function starting. Now I call plot multiple sines because I want to give multiple values of a. So define the range for x. Let's say we have defined from 0 to 2 pi. In the steps of 0.01. I clear the previous plot. Now, here perhaps if you are familiar with a little bit of coding, you understand this word called loop. Just to understand very simply, loop, what it will does is, whatever the a values are there, it will calculate for each value what is y through this formula a sin x. So, you can see for y I is equal to 1 to the number of a values, for each value y is calculated as a sin x. And now, the plot x comma y is given, and use a different style for each curve is what is indicated. You do not need to really memorize all this, you can just copy paste in your graphs. Sometimes you are free to change though. So, you see here that x label is x, y label is y, title is multiple curves for y is equal to a sin x, and you can also add where to add the legend. Then this is your end function. So, this is basically your formula part. This is where is the graphical, how do you want the graph to be represented. Now, again here we want to ask a from the user. So, therefore, ask the user for the values of a. So, now enter the value of a as a comma separated list. So, what we are doing is, we are asking that you enter whatever 2, 3, 4 values of a that you want to enter, but make sure that you separate it with a comma. So, then this is the input that user will give. The code simply converts those inputs to a mathematical array, and then we call this function to plot the curves. So, this is the function to plot multiple sines a values. Now, when you click the save and execute button, okay, which was somewhere in the top here, let us see how it happens. So, enter the values of constant a as a comma separated list 1, 2, 3. So, the values of a, let us say I entered 1, 2. Now, what will it do is, for each a, it will calculate y is equal to a sin x for each x. Similarly, for a is equal to 2, for each x it will calculate y is equal to 2 sin x, like that. Now, if you use that to plot the graph, you can see already that this is how it will be generated. So, this is y equal to 1 into sin x, this is equal to y into 2 sin x. So, you can clearly see the differences, the effect, and so on. So, now let us move to our diffusion problem. How can we write codes for diffusion equation? Again, as I said, let us not really, you do not have to memorize the code as such, but try to see that, understand the code and see what parameters you can change. So, I will show you this. So, for example, carburization problem. We know that carburization problem, you have carburizing gas. So, you have a constant source condition, and the solution is also given like this: C of x comma t minus C naught divided by Cs minus C naught is equal to 1 minus error function x by 2 root dt. Now, quite often in carburization problem, we want to determine either the temperature at which the carburization treatment should be done, this you saw in the previous tutorials also, or the time it may take at a certain temperature, and so on. So, now how do we go about it? So, first is the body of the code itself. Now, what I have done in this code here is that we have taken the C naught, Cs, the temperature, the time, and from the user. So, you see C naught, that means that is the composition of the steel. I want the user to enter this. Cs, what is the surface concentration that is maintained. Now, temperature, at what temperature the carburization treatment is done. Then T values, enter for different times you are interested in plotting, up to what times, for how many time intervals you are interested in doing annealing. Accordingly, you can put the time in days here. So, I have indicated the units also, so and the value unit of time also. Then x we have defined from 0 to 0.01 in this very small steps. Then the temperature, this is just the conversion to Kelvin. Then because we are only entering temperature, so we you remember that we calculate we need D for calculating the profile. So the D can be obtained by the activation parameters which are given here. Q is equal to 200 joule per mole, D naught is equal to 1 into 10 power minus 5 meter square per second, and R is equal to 8.314. And then you calculate the diffusion coefficient, D is equal to D naught exponential minus Q by RT. These are simple just mathematical relations. Here the code is tells you what exactly it is doing, and then you display the calculated diffusion coefficients. Convert time to seconds, since we are putting D in meter square per second. Why we asked in inputs in days is because it is usually easier for user to input in days actually. Now, how do you set up the plot? So, you clear function so that any previous figure was maybe cleared. Then colors. So, I mean this is not necessarily that you need to do, but it would look nice if your plot has different colors for different values. Then these R, G, B, M, C, K represent different colors, you will see shortly. So, just to again emphasize this here I have written in slightly bold font. These are the input parameters, this is unit conversion, these are the predetermined constants, Arrhenius equation, and the appearance of graph. And as I said that we use the loop for different time values and plot C of x comma t for each of the time. And you calculate the concentration profile using the formula that we have given, C naught plus Cs minus C naught into 1 minus error function x by 2 root dt. So, error function is inbuilt, it can calculate the value. And then this is the plotting labeling x, y, and the title. And you can add a legend also, and finally you show the plot. So, now when you so I have highlighted here again what each of these steps is doing. So, now when you want to run this code, so let us say we run this code, the save and execute command. So, first time let us say I enter the initial concentration as 100, surface concentration as 500, temperature at which the experiment is done, let us say I enter 1000 degrees. Now, the calculate diffusion coefficient, it shows as 10 power minus 14. Now, enter the time values as an array. So, let us say I entered 1 day, 10 day, and 100 day. What it shows is, you see, this is the graph we have seen schematically also. Now, this is the red line is for 1 day, green line is for 10 days, blue line is for the 100 days. So, you can actually take this code, put it in Scilab, enter the values, and you will see that this code is generated. Now, how do you make use of this code? You can try something like this. For example, if for this particular steel I want to achieve a case depth of 3 millimeters. Now, you can see clearly that 3 millimeter is barely reached even in 100 days if you anneal at 1000 degrees centigrade. That means 1000 is clearly not enough for this particular combination of parameters to achieve in 100 days at 1000 degrees centigrade. Now, let me see if I change the temperature. If I do at 1200 degrees centigrade, so again C naught Cs is same, temperature I have changed to 1200, and which changes my diffusion coefficient. Instead of 10 power minus 14, now it is 10 power minus 13. Again I enter the same value of time 1, 10 and 100. Now, what you will see is, you see the spread of your profile is changed now, and if you draw this vertical at x equal to 3, you will see 3 mm or 0.03 millimeter. You will see that now you can 100 days are more than enough, you do not need 100 days, almost in 10 days you will be able to achieve your case depth. But you may say, oh, 10 days is even higher for me, let me see if I can try and reduce it further. So, if I try to increase the temperature to 1400 degrees centigrade, now the diffusion coefficient becomes 10 power minus 12. The time values are again 1, 10 and 100, and now you will see that the lines are even more spread out, and my composition now or my case depth now can be almost achieved in 1 day time. Okay. So, idea is not here to now to say ki, this steel requires 1 day, but what I am trying to tell you is that using this kind of your own codes, you can try to understand the influence of various parameters. You can vary the temperature, you can enter different values of time, for example, and you will see, for example, you may say only one temperature I choose 1400, but I give different times. So, that also is a possibility. You can generate your own codes where you vary something else instead of temperature T. You can simply vary the surface concentration and see how the profiles changes. So, the idea is to let you play with these parameters, use the code that I have generated. That code, the body of the code is same for everything, but now you can play with the input parameters and see what is the effect of each of them. So, coming to the last problem, that is the homogenization problem, where the formula is something like this: C of x comma t is equal to 4 C naught by pi summation j is equal to 0 to infinity 1 by 2 j plus 1 sin 2 j plus 1 pi x by L exponential minus 2 j plus 1 whole square pi square dt by L square. So, here again I am not going through this. Here we are giving input initial average concentration. Remember, homogenization is done when you have a dendritic interdendritic structure. You want the overall composition to become uniform. L is equal to your domain length, D is input diffusion coefficient, T is the values in days, J is integer 0, 1, 2, 3. Remember, in the lecture we saw that these terms decrease very rapidly with the increase of j, because there is a exponential dependence. Then you can give the value of x. So, 0 to some multiple of L. So, 4 times L suppose, and then these are the t values. Then setting up the plot, clear any functions, colors, legends. So, you see that these do not change significantly. The look does not change. You may change it for your problem that you are solving. Then this is the body of the main body of the code, where again you see this is the for loop for different values of t, and here this is also for different values of j. So, there are two loops here you will see, because you have different values of j and different values of t. Okay. Then finally show the plot. Now, you see that what happens once you save and execute. So, once I run, then the case 1, let us say I put d is equal to 10 to the power minus 12 and t I see 0.1, 0.5, 1 and 5, and I enter the domain length as 0.01 meters here. Time values are these, and the maximum number of terms j is equal to 0. So, that means I evaluate only the first term. So, you see that here the composition profiles are very close. Okay. There is nothing that has come to average composition. Okay. You still have a sinusoidal variation. So, clearly this diffusion coefficient is too small for any homogenization to occur. Now, what if keeping the diffusion coefficient same, if I increase the time? So, here the time you see that I have put 0.1, 0.5, 1 and 5 days, whereas if I put 1, 10 and 100, how will the keeping everything else same, how will my homogenization proceed? So, you will see that after 100 days you start to see the composition moving towards a more average composition. See, this red is the shortest time, green is then the blue one. You see already the difference. So, here I am studying the influence of time. Now, what I can do? I can see that at the same diffusion coefficient, what happens if I homogenize for 10,000 days, which is of course an impractical thing, but just to see that whether really the composition becomes homogeneous or not. So, you see that 10,000 day is a sufficiently long time where the composition will achieve a average composition. Okay. So, here this is what you can beautifully see the impact of time on the homogenization kinetics. Just to tell you, if we put d is equal to 1 order of magnitude higher, that is 10 power minus 11 if I put, that means now my diffusion coefficient is faster. And now if I put keeping other parameters same, you will see that even in 100 days, compare this here when you have 10 power minus 12, after 10,000 days we were able to see or after the 1000 days we were able to see the constant profile, whereas here by changing one order of diffusion coefficient we are able to see it in 100 days itself. You can try further and say that now I want to reduce one order of or make it one order faster, 10 power minus 10. Now, you will see that even in 10 days you can achieve a horizontal profile. So, this is how you can understand the impact of several parameters. You can change the length here, you can change concentration, and this d, in fact, like previous carburization example, instead of input d, you can use in your code temperature and calculate the diffusivity and so on. So, various things. So, I encourage you highly to use this codes, download Scilab and generate your own codes and plot for yourself these various diffusion equations and see for yourself, get some hands on experience on how the parameters influence the diffusion profile. So, hope you will practice that. Thank you, and we will continue further with our lectures.